Low-cost experiment to determine the correct relativistic energy formula by David C. Lush. Abstract. Motivation and a description are developed for an experiment to determine which of two alternative expressions for the relativistic energy of a massive object is correct. One form is the relativistic energy formula of Einstein's special theory of relativity, considered well established and found ubiquitously in modern physics textbooks. The alternative energy formula, proposed by Osiak, is based on integration of the covariant Minkowski equation of motion, in contrast to Einstein's use of the three-dimensional Planck equation. Osiak's formula differs from Einstein's by a relativistic factor divided by 2. The mass-energy equivalency is thus halved, while the relativistic energy becomes quadratic in the relativistic factor. The additional relativistic factor compared to Einsteinian relativity, in addition to implying the energy of highly relativistic particles is greatly larger than previously thought, also allows that the relativistic factor may be negative without requiring existence of negative energy states. Although Osiak's formula implies as well that energy is not conserved in relativistic particle collisions, energy non-conservation might account for anomalous observations, such as accelerating cosmos expansion and cosmic inflation. Osiak's energy expression may also be useful in accounting for observations of anomalous galactic rotation that have led to the hidden matter hypothesis. Recently, Osiak has suggested that the formulas of the special theory of relativity related to the energy of a moving body, derived by integrating the three-dimensional Planck equation of motion, are inconsistent with the first principle of relativity, Lorentz invariance of physical law. Osiak derives relativistic energy and the mass-energy equivalency using instead the Lorentz covariant Minkowski equation, arriving at significantly different results. The mass-energy equivalency is halved, and the energy of a moving particle is multiplied by a relativistic factor divided by 2, compared to traditional relativity.
Various additional features of Osiak's form of relativity are plausibly of interest to physics generally. For example, it is straightforward to demonstrate that Osiak's relativity leads to violation of energy conservation in relativistic particle collisions. This fact may be taken in part as supporting the correctness of Osiak's energy formula derivation, assuming validity of the Minkowski equation of motion, in that it is established physics that Einstein's relativistic energy formula is unique in conserving energy in relativistic collisions. It also may account for Einstein's choice to determine the relativistic energy from the Planck equation of motion rather than the covariant Minkowski equation, as integration of the Planck equation is the only procedure that obtains energy conservation in relativistic collisions. In the present day, however, energy non-conservation may be useful in explaining the origin of dark energy, as well as that of cosmic inflation. Therefore, it is important to not dismiss Osiak relativity on this account alone. Also, the principle of temporal momentum conservation, equivalent to energy conservation in Einstein relativity, remains valid in Osiak relativity.
It is reasonable to be skeptical of a proposed alternative to a well-established theory such as Einsteinian relativity. However, apart from the existence of the unexplained physical anomalies of dark energy and apparent dark matter, it is important to recognize that Osiak relativity reproduces Einsteinian relativity in all aspects, apart from relativistic energy. While the relativistic energy formula is modified, relativistic concepts of spacetime, kinematics, and particle mechanics are preserved, and Osiak's relativity is fully consistent with the explicit relativistic principles of Lorentz invariance and a limiting velocity identical for all observers. Importantly, all of Maxwell-Lorentz electrodynamics is unaltered and remains expressible in covariant form. Other features, however, exist within Osiak relativity that give it a richness beyond traditional relativity. For example, just as spatial components of the momentum vector are signed, Osiak relativity, by decoupling the temporal component of form momentum from the energy, allows temporal momentum to be negative while energy remains positive definite.
Allowing temporal momentum to become negative has significant electrodynamic implications. A negative temporal component of electromagnetic field 4 momentum implies electric and magnetic field spatial components are imaginary quantities. The imaginary time-reversed fields exist in addition to the well-established real, retarded, and advanced solutions to the electromagnetic wave equation. Such imaginary, time-reversed electromagnetic fields may be useful in developing a new understanding, for example, of the complex character of quantum mechanics.
Applied to the present subject of the possible correctness of Osiak's relativity, the concept of time-reversed imaginary fields leads to a requirement that every real charge must have an imaginary character, according to an observer of time-reversed radiation from it. Assuming the positron has an imaginary negative charge and moves in an imaginary field, obtains that a different behavior is expected than if its charge is real and positive. This change in positron behavior under a steady applied magnetic field is readily experimentally distinguishable from expectations according to traditional relativity.
Section 2. Overview of Osiak relativity. Osiak argues Einstein's use of the three-dimensional Planck equation of motion in determining relativistic energy is inconsistent with his postulate of Lorentz invariance of physical law, and instead derives formulas for relativistic kinetic and rest energies from the covariant Minkowski equation of motion. Thus, it is reasonable to refer to his proposed form of relativity as Einstein-Minkowski-Osiak relativity. It will also be referred to herein simply as Osiak relativity. The stated two postulates of Osiak relativity are Lorentz invariance of physical law and Lorentz invariance of the speed of light in a vacuum. These are the same two fundamental postulates of relativity identified in standard textbooks, but an additional, implicit postulate of energy conservation is not used in Osiak relativity. An energy conservation postulate, with conservation of momentum derived from the two relativity postulates, is used, for example, in the widely used classical electrodynamics textbook by J.D. Jackson, to derive the Einstein relativistic energy formula and the quantity that is known in Einsteinian relativity as the energy-momentum 4 vector. In Osiak relativity, the 4 momentum vector is identical to that of traditional relativity, but the energy-momentum 4 vector does not exist. Integration of the work done by the Minkowski force acting on a particle initially at rest obtains directly that the mass-energy equivalency for a particle is half the familiar Einsteinian formula, while that the total relativistic energy is the Einstein value multiplied by a relativistic factor divided by 2. The total relativistic energy is thus quadratic rather than linear in the relativistic Lorentz factor. Finally, the kinetic energy, as in Einstein relativity, kinetic energy is total energy minus rest energy, but unlike in Einstein relativity, using Osiak total and rest energy formulas obtains the familiar relation for kinetic energy from classical physics. Given that relativistic energy is larger in Osiak relativity under conditions where velocities approach the speed of light, it is natural to wonder what prevents a proliferation of particles created inconsistently with observation, in particle accelerator or cosmic ray collisions, in the absence of an energy conservation principle. Such proliferation is not expected according to Osiak relativity because it conserves 4 momentum, and the form of the temporal component of 4 momentum is unchanged from that of Einstein relativity and conventional Maxwell-Lorentz electrodynamics. According to Osiak relativity, it is incorrect to refer to the 4 momentum as the energy-momentum 4 vector. However, separate conservation of temporal momentum is valid in Osiak relativity by the same arguments that prove conservation of energy in Einstein relativity. Therefore, the traditional relativistic energy, which will be referred to herein as the Einstein or quasi-energy, being proportional to the temporal component of 4 momentum, remains conserved. It is essential to plausibility of Osiak relativity that the temporal component of 4 momentum is unchanged from its familiar Einsteinian value. This implies all observed particle creation threshold effects relatable to the Einstein rest energy can be reinterpreted as following from conservation of the temporal component of 4 momentum. All that is needed is to account for the inverse factor of 2 on particle rest energy that occurs in Osiak relativity. The factor of 2 is apparently an alternative way of resolving the spin-orbit coupling anomaly to the usual method based on Thomas precession. What changes in Osiak relativity is the relation of temporal momentum to particle relativistic energy, with the temporal momentum becoming proportional to the square root of relativistic energy. Thus, Osiak relativity, like Einstein relativity, conserves for momentum, but does not require or impose an additional postulate of energy conservation. Osiak argues it is more faithful to the relativity postulate of Lorentz invariance of physical law, in that it is based on the four-dimensional Minkowski equation of motion, rather than the three-dimensional Planck equation.
Osiak relativity makes possible a unified description of particles and antiparticles as simply two aspects of particles, of temporal orientation, with or against the positive direction of time of a particular observer, reference frame, or particle. What are particles in one frame are antiparticles in another of opposite temporal orientation. Therefore, it is useful to adopt a more neutral terminology, without a favored temporal direction. That is, a particle may have either temporal orientation, while a particle with a positive Lorentz factor in a particular reference frame may be identified as a coparticle in that frame, and to other particles or observers with similar temporal orientation. Thus, an electron is a positron in a reference frame with inverted temporal direction to that of the laboratory frame. In both Osiak and Einstein relativity, the relative direction of temporal momentum of a particle in a particular reference frame is determined by its Lorentz factor sign. However, only in Osiak relativity is the particle relativistic energy positive definite independent of temporal orientation.
Section 3. Antimatter as time-reversed matter. Dirac's relativistic quantum theory of the electron predicted both the electron intrinsic spin and existence of negative energy electron states, now regarded as anti-electrons, that is, positrons. These unique features of a fundamentally relativistic description of the electron are intimately connected with the expressions for kinetic and total relativistic energy of a material particle as according to Einstein's special theory of relativity. Osiak relativity provides a useful description of antimatter as particles with negative four-momentum time component, without also implying negative rest energy. Osiak relativity obtains that total energy in, say, an annihilating matter-antimatter collision remains positive definite even though the total temporal momentum may vanish. For example, suppose an electron and a positron with equal and opposite ordinary velocities collide. With the positron assigned a temporal component of four momentum based on allowed solutions to the Dirac equation, and the electron temporal momentum of equal magnitude but positive, then after the collision all components of the total four momentum vanish, including the temporal component that contains the total energy according to Einstein relativity. Dirac proposed that the positron represented an empty state, or hole, in a sea of filled electron states so that energy is liberated in accordance with observation, due to the electron falling from its initial free state to the final state filling the empty hole, and while also not allowing all electrons to fall into lower unoccupied states. The vanishing of total temporal momentum in simultaneity with energy liberation is, on the other hand, not a similar problem according Osiak relativity, where the time component of four momentum is distinct from the energy. In Osiak relativity, unlike traditional relativity, the total energy after the matter-antimatter collision of actual particles as described above need not vanish. If a particle with an internal clock, as hypothesized by de Broglie, has a negative time component of four momentum, it moves according to its clock oppositely along its world line, toward the past, compared to another similar particle with positive time component of four momentum. Applying the concept of a negative Lorentz factor as an explanation of antimatter is arguably parsimonious, as it requires no other novel quantities, such as a new type of positively charged particle or negative mass. A negative Lorentz factor has been used previously to describe antimatter, including in physics textbooks. Stuckelberg's concept of antimatter as matter traveling backwards in time, later taken up by Feynman, was apparently considered plausible enough within Einstein relativity. Feynman wrote about it extensively and incorporated negative Lorentz factors implicitly in his approach to relativistic quantum mechanics. Feynman's rules, stating that 4 momentum terms for antiparticles are to be subtracted from the total 4 momentum term in Dirac delta function factor of amplitude terms of Feynman integrals, and reversal of arrow directions for antiparticles in Feynman diagrams are equivalent to assuming negative Lorentz factors. As already noted, classic relativistic quantum theory textbooks also assume negative Lorentz factors are associated with antiparticles. Yet, later authoritative review literature on pair production makes do without them. Perhaps this is due to the problematic character of Lorentz factors applied, such that the proper momentum of antiparticles is inbound to the creation event, as viewed from the laboratory frame. According to Osiak relativity and assuming antimatter is described by negative definite Lorentz factors, there is no difference between a particle and its antiparticle in its rest frame. It therefore seems appropriate to adopt a more neutral terminology for describing matter and particles of matter in frames, including time-reversed frames. Matter and particles of matter with positive Lorentz factors will thus be referred to herein as comatter and coparticles, respectively, when it is useful to distinguish them from matter and particles of matter with negative Lorentz factor in a particular reference frame. Section 3.1 Pair Creation in Osiak Relativity. Electron-positron pairs from cosmic gamma-ray photons collisions with atomic nuclei were first observed in 1932, visualized in cloud chamber photographs. The electron and positron leave condensate trails, while the target nucleus and incoming photon are not directly observed. In the initial interpretation of such an event, the positron was assumed to have a positive Lorentz factor and positive charge, and the photon world line ends at the creation event while the positron and electron world lines both begin at the event. In an applied magnetic field, the electron and positron undergo cyclotron motions in opposite directions while diverging from the event, as predicted according to these assumptions. In order to better understand such a pair creation event, it is useful to assess it from a momentum conservation perspective. Momentum calculations are most easily performed in the center of momentum reference frame.
In the center of momentum frame, the total momentum of the gamma-ray photon and atomic nucleus is initially 0. After the event, the nucleus recoils oppositely to the total momentum of the electron-positron pair, so the total momentum continues to be 0. Assuming positive Lorentz factors on both the electron and positron, both particle world lines must originate at the event. The particles diverge from the event with apparently random speeds and angles, as allowed by quasi-energy conservation, while the nucleus diverges oppositely so as to conserve momentum. Created particle motions observed in the cloud chamber are consistent with expectations, based on the assumed negative and positive charges, and both particles of the electron mass, moving as expected in the magnetic field of known strength.
Section: Test Apparatus and Conduct. The proposed test apparatus is illustrated notionally on Figure 4. The test apparatus consists of a gamma-ray photon source, a collimator pipe, a vacuum chamber containing a metal foil target, followed by a second pipe, the runout, also within the vacuum environment containing the target, which opens into the runout pipe along the direction of the collimated photons. The runout pipe opens in turn into a second vacuum chamber that is immersed in a steady magnetic field generated by a large electromagnet. The strength of the magnetic field is set as necessary to oppositely divert created electrons and positrons toward their detectors, also contained in the vacuum environment. The gamma photon source is a betatron, a synchrotron particle accelerator of beta particles, that is, electrons. A betatron is ideal for the test in that it can create adequate quantities of gamma-ray photons through the magneto-Bremse-Strahlung process, also known as synchrotron radiation. The betatron can produce photons of sufficient energy as needed to create electron-positron pairs when scattered by metal atoms nuclei in the foil target. Gamma photons that are aligned in the direction from the foil target to the deflection magnet field center are selected by the collimator metal pipe. By conservation of momentum, electron-positron pairs from photons with sufficient energy beyond the electron-positron pair creation threshold will continue close to the direction of the photon, so as to arrive near the center of the deflection magnet. The runout's purpose is to add a travel time delay to the created electrons, which may be as well a time advancement on positrons if they are correctly described as time-reversed electrons, created at the event of the gamma photon being scattered by the target nucleus. The required length of the runout pipe is determined based on the time resolution and accuracy of the electron and positron detectors. That is, the runout duration, that is, the transit time of the electron or positron through the pipe, has to be of the order of at least the time resolution or accuracy of the detectors, as required to determine if the time between positron and electron detection is roughly twice the transit time through the runout. If the positron is moving backward in time from its creation event, the transits through the runout of the positron and electron each add to the total time difference of detection of the positron and electron, with the positron detection preceding that of the electron. Thus, supposing the measurement, accuracy, and resolution of the detectors is about 2 nanoseconds, then the transit time through the runout must be at least 1 nanosecond. Since the created particle speeds are upper limited by the speed of light, the necessary runout length is about 0.3 meters. Of course, reduced resolution or accuracy of positron or electron detection's timing increases the necessary runout length proportionately. However, a longer than necessary runout can be fully compensated in the detection correlation processing and increases significance of positron detections prior to their creation if such occur. The steady magnetic field created by the magnet deflects electrons toward the electron detector and positrons toward the positron detector. The detectors establish the time of each particle arrival at the detector to within a defined tolerance. Each detection of an electron or positron and the measured time of the detection is reported to the detection correlator, which processes the stream of detections for near coincidences and also for positron and electron pairs that meet a criterion of positron time advancement by twice the propagation time through the runout. According to Osiak relativity, it is expected that all positrons are detected twice the runout transit time prior to the corresponding electron of the pair. According to Einstein relativity, all successful electron-positron pair detection correlations will be simultaneous within the expected tolerance based on detection time accuracy. Concluding remarks. Stuckelberg's idea of the positron as an electron with a negative Lorentz factor, and so moving toward the present from the future, was taken seriously by Feynman and is a fixture of quantum electrodynamics, yet it is not evident in authoritative accounts of pair creation and seems to be contradicted by standard momentum conservation diagrams. A positron moving from the future toward the pair creation event is not supported by observation. Also, the positron as an empty state in an otherwise filled C cannot exist until after the event of creation. In the description from whole theory, the positron both exists only after the event and has proper momentum directed toward the event. The momentum conservation diagram for whole theory thus differs from the pair production standard literature in the direction of the recoil. Combining Dirac theory with the relativistic energy equations proposed by Osiak can reproduce standard momentum conservation diagrams while requiring use of a negative Lorentz factor to describe the positron. It can further provide a description empirically distinguishable from both the Feynman calculus and the pair production literature. That is, it predicts that annihilation of a positron occurs prior to its creation, according to a laboratory observer, and has proper momentum away from the event. This is significantly and measurably different from the Feynman description of the positron as a time-reversed electron coming from the future and reversing temporal momentum direction at the event. In the Osiak description, the positron and electron are both created at the event, and the positron temporal momentum is opposite that of the electron, but they do not simultaneously exist according to the laboratory frame observer. This prediction may be used to falsify one theory or the other. Osiak's proposed alternative formulation of relativity theory is based on, and fully consistent with, Einstein's principles of relativity and the Minkowski equation of motion. According to standard textbooks that acknowledge implicitly or explicitly that other energy formulas are also consistent with the relativity principles, it may be considered a valid alternative form of relativity that has been rejected on account of energy conservation violation, because only a relativity version that is expressible in Lorentz covariant language is fully consistent with the first relativity principle, Lorentz invariance of physical law. It might also be referred to as corrected relativity, and if it is validated by the experimental procedure described herein. Low-cost experiment to determine the